All right, so here we're going to talk about wave functions, and wave functions can be a real fun treat if you're first encountering them because they're kind of different. As chemists, they can be a little bit weird because it's not something that we just go out into the lab and measure like we would other variables. So we're going to have to be mindful of that and figure out what do they mean, how do we use them, what do we need them for, and why they're important. All that fun stuff. So a couple important properties here. As the name might imply, wave functions, it is a function. It is a mathematical equation that we're talking about here. So it could be something like our wave function y equals mx plus b. That's all we're talking about. It's some sort of an equation here. Now, up here, mx plus b, we probably all recognize that as a linear trend that we've used before. What does a wave function do for us? Well, the wave function, which we're going to denote with psi here, it denotes the three-dimensional properties of electrons that are around an atom. We can also take this to molecules if we really want. We won't have to deal with that too much for this course, but that's where this does go. One of the really important things that we have to be mindful of here is this is just an equation. And so it can be a lot of things that we're not used to. Specifically, psi has no physical meaning. This is often something that shows up in standardized exam. They'll say, what is the physical meaning of psi? Always no, that's a trick question. There is no physical meaning. It's just a function that tells us about properties, but it doesn't have any actual physical interpretation in its form as shown. Where we do find physical meaning is if we square the wave function. So psi squared has meaning. And what is this meaning? It's the probability of finding an electron. Specifically, we're going to be thinking about in three-dimensional space is the property that we're going to be often looking for. So that's what we'll be often thinking about here. So that's the trick here. Psi itself has no physical meaning, but if we square that, we find out that it tells us the probability of finding that electron somewhere in space. The way we'll often be seeing wave functions split up for us is in this format here, where we say that psi is a function of r, which is in coordinate space r, times a, which is in coordinate space theta and phi. So feels a little bit simple and ridiculous at this point, but we're going to get into more of what these mean here a little bit later. R of R here, this is what we call the radial component, and really its function is to tell us about the size. So in other words, when we're thinking about where can we find an electron in three-dimensional space, how far from the nucleus are we? So remember, if we're thinking about polar coordinates here, we have a point out in space that we define. It has coordinates of r. That's what the radial function is dealing with. It says, where are we in r space? Whereas if we look at A here, we'll refer to this as the angular component, and it's dealing with both of the angular variables, theta and phi here. This is a more complicated function in some sense, but really it's really simplistic because we've seen this a million times before. It tells us about shape. Specifically, it tells us, are we in an s orbital, a p orbital, a d, an f orbital? And hopefully we remember all of those shapes. You know, our s, our sphere, the p orbitals that we dealt with in organic quite frequently that look kind of like the dumbbells. For inorganic, we're going to start thinking about d orbitals that start to look like a flower shape. So we'll think about what do those mean here a little bit later. But that's all it's telling us. What shape are we looking at? And since they are these different shapes, they have a difference in their angles, and that we'll see how we define them. So that's why they are in theta and phi space. Both of these functions, radial and angular, are built off of functions that are understood mathematically. We'll see a little bit of these forms a little bit later here, but we're not going to spend a whole lot of time dealing with the math. The big thing that we need to be able to do is look at them and say, okay, what does this tell us? What does it mean in three-dimensional space? Now, in general, wave functions for atoms or molecules, they do have some properties that we have to be aware of. For example, if we have a function psi, it must be single-valued. So what I'm saying here is if I put it on a plot, something like this, is fine, because we see that for any value on here of x, there is only one value of y. An example where we would have a wave function that's improper, something that's not allowed, is if I had something that looked maybe like this. This is not a function that we like, because, for example, if I look here, x has two unique y values. That is not appropriate. We cannot have a function of that form. That would be something that we would say no to. It's because it's not single valued. Okay, that's what single value means. Second property that must be fulfilled is if we look at our wave function, it must be continuous and have a continuous first derivative. So, for example, if I did something like this, where it goes to a sharp point and then comes back, at the top here, we would say, wait a minute, we have a problem. It's discontinuous here. So this is not an allowable function that we could use here. So basically what it means when we're looking at different plots is that we're going to have smooth functions, things that don't have sharp points to them, things that don't have things, for example, like plateaus or square tendencies to them. Those are bad. So that is what I mean by it must be continuous. Third property that we'll have is that no matter what our wave function is, it must approach zero as we head towards r of infinity. So as we go out farther and farther, what we should expect is that that wave function should somewhere at infinity be zero. So this is a limit law type of thing, if you remember those. But basically saying that, hey, if we go to infinity, we have zero chance of finding that electron way out there, so it has to approach zero at infinity. Last two properties here are more easily expressed through quote-unquote simple mathematics. First, all wave functions that we use must be normalized, which says, hey, if I take the wave function, multiply it by its complex conjugate, so basically, essentially, we're squaring the wave function here, and we integrate that over all space, that's what d tau is telling us, that integral must be equal to 1. This is about thinking about the probability, which is described by, for example, psi squared. We need to have that. So if that is how we find out that, hey, if we look at all of our wave function, we're guaranteed to find the particle. So again, it's a more mathematical thing. We'll talk more about that as we go along, but that's what it means. Second piece that's mathematical is that our wave functions must be orthogonal. That says if I use two wave functions for a molecule here and I multiply them together, integrate again over all space, it must come out to zero. So it says that no wave function is a part of another one. Again, these are the mathy ones that I'm not going to spend a lot of time on. This is something, again, you learn more strenuously in PChem. Don't worry about it right now. They're just some pieces of the math. When we need them, I'll explain them in more detail. These are the ones that are more important for us right now. Those are the easy ones to see because we can throw them onto a graph. We can see what they mean pretty easily. All right, so that's what we've got for right now for wave functions that you need to know. Again, we'll be talking more about these as we go forward. So as always, if you have questions, concerns, let me know. We'll get you taken care of. We'll make sure that we got all of your questions and curiosities answered. All right, that'll do it. Till next time, be excellent to each other.